Hi, professors and PAs of CSCI544, and today we're presenting on behalf of Team 32. My name is Julian Yu, and I'm presenting with my teammate, Team Yu Zhang. Let's begin. Our topic is about how the transformer could potentially be improved across the different NLP task categories. The transformer was first introduced by the famous article Attention is All You Need and has led to tremendous advancement in the domain of natural language processing, aka NLP. Those novel ideas such as masked multi-head self-attention have greatly improved the performance metrics in routine machine translation tasks. As of today, many state-of-the-art models in NLP are still built upon the transformer. So as a result of the transformer's remarkable success, ever since the publication of Attention is All You Need, there has always been numerous attempts to fine-tune the transformer on different types of NLP tasks, including machine translation, language understanding, abstractive summarization, and question answering. However, we find out that there are still many other NLP domains where the outcome of modifying the transformer remains unknown. To fit within the scope of this course project, we decided to mainly focus our experiment on a natural language inference, aka an NLI task, from Stanford. Meanwhile, we studied two English-Chinese translation datasets because first, we still want to show the generalizability of our result on conventional machine translation tasks. And second, machine translation is a subtle and interesting task to evaluate. So I will then leave the modeling part to my teammate.
As what you had said before, we aim to explore how modification of hyperparameters and layers could affect transformers' performance metrics in a variety of NLP texts to answer two questions. First one is that the modification to our transformers result in significant improvement on other NLP texts that have not been covered by the paper written by Naran et al. In 2021. To answer this question, we introduced the natural language inference text in discovering this puzzle. And the second question is that could we further push the performance boundary of transformer by capturing the local and global dependencies? And our method is we exchange the feed-forward neural network in a sublayer in the transformer with a convolutional neural network sublayer. The motivation here is that a vanilla transformer does not take into account the relative distance among words, and that is substitution. And that substitution with convolution layer might work as a remedy to such as drawbacks by concentrating solely on local dependencies. However, global dependencies are still out our interest, and that we are like to take that into our account. As a matter of fact, instead of embracing fixed middle size given by the CNN structure, we're looking at a whole sentence. We propose distance mapping and attention and replacing CNN structure with diffusion gate. Distance map, well, distance map in its meaning is mapped multi-head attention rather than the standard attention. In addition to the simple distance map inspired by IM and Cho in 2017, we also introduced the forward and backward messages by Shen et al. In 2018. In particular, the word distances are weighted and well considered in the modified transformer, allowing the model to underscore the local dependency without undermining the global dependencies. And the diffusion gate resembles the gate structure of LST and is placed right after the max multi-head attention. The purpose of this is to encode long-range dependency from both the forward and backward direction as a complement structure toward the forward and backward mask. And the experiment setting is about using the pre-trained word embedding without fine-tuning GloF A40B300D1, and the optimizer we use is Atom, and we implement the whole code in PyTorch. Result and discussions. For natural language inference, the result shows that when we use torch.n nonlinear as a feed-forward layer, the existence of distance map does not influence testing accuracy. If we use torch.n and column 1D instead, its performance with distance map is slightly worse than that without distance map. The results show that even though column 1D and layer are theoretically the same, there are actually some minor differences in practice. without distance back, the result of column 1D and linear are close enough. For example, only 0.1%. When we include a distance back, the difference becomes negative 0.4%. From machine translation tests, the result shows that when we use linear layers, having a distance back is better than without a distance back. When we use 1 gram, this difference reached 2.41%. Even with the increase of the gram size, the difference decreased, but it's still above 1%. However, using column 1D instead, two models are tied up. It doesn't show significant advantages among models comparing linear and column 1D. No matter whether we have distance back or not, column 1D is better than linear. Discussion. In machine translation task, distance back shows its advantage, which has roughly 2.4% difference in 1 gram. However, the NLI test does not show huge advantage using distance back. Even column 1D without distance back has highest accuracy. And the NLI has is insignificant using a distance back, and this is highly due to its majority sentences are short. And for machine translation text, there's an evaluation metric problem. The blue score cannot semantically capture the entire meaning of the translated sentence. Conclusion. We analyze the significance of word distance under two different texts, NLI and machine translation from English to Chinese. And secondly, we use the distance map to capture the local dependency without losing the ability to capture the global dependency. And thirdly, we researched the real-world difference between